How does quantum error correction work in quantum computing? Have you ever wondered how quantum computers manage to keep their information intact despite the many challenges they face? Let's break down the fascinating world of quantum error correction and see how it works. Quantum error correction is all about protecting the delicate information stored in qubits. Unlike classical bits, qubits are fragile and can easily lose their quantum state due to noise and other factors. This makes error correction essential for reliable quantum computing. At the heart of quantum error correction is the idea of redundancy. A single logical qubit, which is the quantum equivalent of a classical bit, is encoded into multiple physical qubits. This means that even if some qubits experience errors, the overall information can still be preserved. So how does this encoding work? First, the logical qubit is represented by an entangled state of several physical qubits. This spreading of information allows the system to identify and correct errors without directly measuring the quantum data, which could disrupt it. Next comes the syndrome measurement. This step involves performing special measurements on parts of the system to detect errors. These measurements do not reveal the actual quantum information but instead indicate which errors have occurred. Once the errors are detected, the next step is error diagnosis and correction. Classical algorithms analyze the syndrome information to figure out the most likely error pattern. They then apply corrective operations to restore the logical qubit to its intended state. One popular method used in quantum error correction is called surface codes. In this approach, qubits are arranged on a lattice, and local interactions help detect errors. The larger the code, the better the error detection and correction capabilities become. Recent experiments have shown that logical qubits can maintain coherence longer than individual physical qubits when using these codes. For quantum error correction to be effective, the physical qubits need to have error rates below a certain threshold. If the error rate is too high, adding more qubits can actually make things worse, as errors accumulate faster than they can be corrected. Once the error rate is below the threshold, concatenated codes can be used. This means nesting quantum error correction codes within each other, which helps suppress error rates exponentially. This process is vital for scaling quantum computers to practical sizes. It allows quantum devices to overcome the natural noise and imperfections of hardware, enabling longer computations and more complex algorithms. These algorithms could potentially break classical cryptography or simulate intricate quantum systems. Implementing quantum error correction requires high-quality qubits and fast classical processing to decode syndrome measurements in real time. This ensures that errors are corrected quickly before they can accumulate and cause issues. In essence, quantum error correction works by encoding quantum information across multiple qubits, detecting errors through indirect measurements, and applying corrections based on classical inference. This process is fundamental for achieving reliable and large-scale quantum computing.